What are the different types of radioactive decay? Well, there are three types. The first type is called alpha. So we can write an alpha particle, sort of like, you can notate it as this, or alpha, the Greek symbol, or an alpha particle is very much like a helium atom, so we can also designate an alpha particle as that. So let's pick a radioactive element. Let's say uranium-242. This is uranium, and it's going to go through an alpha decay, which means it'll produce an alpha particle. So here is our alpha particle. It will also produce another element. To figure that other element out, we have to make sure that its atomic mass, when added to 4, this plus this, must equal 242. So obviously our element is going to be 242 minus 4, so this will be 238. And to figure this number out here, its atomic number has to equal this atomic number plus this must equal 92. So this has to be 90. And if we look in the periodic table, element with atomic number 90 is thorium. So that means when uranium-242 goes through an alpha decay, it produces helium and thorium-238. Let's pick another example. Let's say we have radon. Let's call this 230 radon. And it's going to go through an alpha decay. So what is our other product? Again, 230 minus 4 is going to be 226, and 86 minus 2 is equal to 84. An element with number 84 as atomic number is polonium. So that is our answer. When radon goes through an alpha decay, it produces an alpha particle and 226 polonium. The other type of radioactive decay is beta decay. So beta, or we can designate it as the Greek symbol beta, or it can be thought of as an electron. A beta particle is very much like an electron. So let's pick our element that'll go through a beta decay. So let's pick again 242 uranium. It'll produce a beta particle. And again, what is the other product? We do the same mathematical calculations. Again, the atomic mass has to add up to 242. So obviously this is going to be 242 here. And the atomic number has to add up to 92. So this has to be 93, because 93 plus a negative 1 is equal to 92. So our element with atomic number of 93 is neptunium. So this is what happens when uranium goes through a beta decay. It produces a beta particle and 242 neptunium. Let's take another example. Let's go to radium. Let's pick radium-240. Let's go through a beta decay with radium. Again, it's a beta particle. And again, the number here must be 240. 240 plus 0 is 240. And this must be 89, because 89 plus a negative 1 is 88. An element with atomic number of 89 is actinium. So the products for our radium-240 beta decay is a particle of a beta particle and 240 actinium. The last type of radioactive decay is called gamma decay. So gamma, but usually it's given by this symbol, gamma. And a gamma particle is very much like a photon. It's very small. It's smaller than an electron, and it has no charge, but it is very high energy. So let's take our uranium-242 that is going to go through a gamma decay. Since a gamma particle has basically small in size and has no charge, that is how it's designated, with a zero atomic number and a zero atomic mass and a zero atomic number. So the question is, what's the other product that it forms? Well, again, if you do the mathematical calculation, you'll find that it looks like nothing happened. You still get a particle that looks like uranium-92. But something happened inside the nucleus of this uranium atom, okay? So something did happen. It's just in chemistry, we look at the macro picture. So if you want to know about gamma decay, you have to go into quantum physics to find out what's happening inside the nucleus of the uranium. But something did happen that is different from this starting material here. So again, if we take another example, let's take 227 actinium, and it goes through a gamma decay. Again, it looks like here that the actinium did not do anything, but like I said, it did do something at the subnuclear level, okay? So this is what happens when we go through a gamma decay. Now, in the beginning of this lecture, I said that there was only going to be 3 types of radioactive decay, but I feel like I should add 2 more types of radioactive reactions. Some teachers do not go over this, but I feel like for SAT chemistry, for honors chemistry, you do need to know this. So the other type of decay is called a positron. So a positron particle basically has the same properties as an electron, but instead of a negative charge, it has a positive 1 charge. So we can write it as this, or we can write it as this. So this is a positron particle. So let's take our uranium-242, and we'll go through a positron decay. Again, the mathematical calculations are the same as before. So this must be 242 for our other product, because 242 plus 0 is 242. And here this must be 91, because 91 plus 1 is equal to 92. So the element with atomic number of 91 is protactinium. So taking another example, let's say we have fluorine. Let's say fluorine 20. And it goes through a positron decay. So our other product would have to be 20. 20 plus 0 is equal to 20. And this has to be 8. 8 plus 1 is equal to 9. So element with an atomic number of 8 is oxygen. So the products when 20 fluorine goes through a positron decay is a positron particle and 20 oxygen. Okay, so the last type of nuclear reaction is not a decay, but it is an actual, that particles actually used as a reactant. For example, it's called electron capture. So electron capture is exactly how the name implies. is when an element is actually capturing an electron. So let's take our radon element here. Radon has an atomic number of 86. Let's call it radion 230. And it goes to electron capture. It'll capture a electron particle. And what is now the product of an electron capture? So again, as before, we do the math. 230 plus 0 must be 230. 86 minus 1 is 85. So our product has an atomic number of 85, and that is astenine. Okay, let's do another example. Let's say we have nitrogen 16 that will capture an electron. What is the product? And our product is going to be 16 carbon. Okay, so this is called an electron capture.